Good morning. Welcome back to day 2 of our conference. So I hope you left yesterday feeling inspired and more knowledgeable by the possibilities that we explored. Today is not just about imagining the future. It's about owning it and building it and being bold enough to be a leader. So speaking of leaders, I'm thrilled and honored to introduce our keynote speaker, Dr. Nina Kottler. She's been a practicing radiologist for over 20 years. With her clinical experience combined with a graduate degree in applied mathematics and optimization theory, she has been using technological innovation to improve quality and drive value in radiology. As the first radiologist to join Radiology Partners, Dr. Kottler has held multiple leadership positions within the practice. Currently, she is their Associate Chief Medical Officer in Clinical AI, serving on the Innovation Steering Committee and working groups, and is leading the Data Science and Analytics Division of the Clinical Value Team. As Vice President of Clinical Operations, Dr. Kottler also developed and practices in Radiology Partners' Remote Imaging Division, serving internally on their AI, IT, and Culture and Leadership Support Boards, and runs the Education and Development Affinity Group for Radiology Partners Belonging Council. And speaking of being bold enough to be a leader, in 2018, she received the Trailblazer Award, which is an award recognizing a pioneer female leader in the field of imaging informatics. I asked Dr. Nina what she's most passionate about. And with all of her past and present accolades, her answer wasn't about titles or achievements. It was about reading and learning new things, such as how to be a better human being. I got chills then, and I just did now from hearing this. So I'm truly honored that she's here with us today. So please help me welcome Dr. Nina Kottler.
Thanks, and thanks everyone for being here on a Saturday. I'm excited to talk to you guys today. You know, I've been thinking for a while that we have a massive call to action right now in healthcare. We have not enough physicians to manage the amount of work that's coming at us. And the burnout rate of physicians is escalating. In radiology on its own, it's at over 60%. 60% of the radiologists are burnt out. And we have a tool that can help us. Artificial intelligence has the capability to do a lot of things. And so why aren't we seeing it deployed everywhere? That's what we're going to talk about today. So Mel asked me to speak about an article that I helped write. And this article is, here's my disclosures. This article is called Developing, Purchasing, Implementing, and Monitoring AI Tools in Radiology, Practical Considerations. It was actually a multi-society paper. There were 2 people from each of the different societies that got together and wrote this. And the paper has quite a few different sections in it, 9 different sections. And if you delve into it more, there's 27 individual components of that. It's quite a dense paper with lots of information, and that's the kind of thing that would be great for this kind of scientific session. But in thinking about what I wanted to present to you, I wanted to try to get across a couple of ideas. Idea number 1. One of the things that I find is quite difficult sometimes is translating information that's done in the laboratory to a clinical use, right? Point of care, what are we doing day to day? And that translation needs to happen. And I want to try to do that for you today about that article. The second thing is that things are evolving so quickly in technology. And normally in technology, we're not tip of the spear in healthcare. We're usually laggards. In fact, we're like 10, 15, 20-year laggards. We know the direction we're going to go because every other industry has already gotten there before us. But not now. Artificial intelligence, we are using before a lot of other people. And this means that healthcare is now driving the pathway for how we're going to do it for our patients. And with it, it's evolving quickly, and we're evolving quickly with it. So a lot of the things that are written in that paper, some of them might already be out of date. So I want to present to you some of the newer stuff that we've been working on and what we've been seeing. I always like to start with this kind of picture because I find it's really helpful in understanding the maturity of a new technology. So if we look at where at least the AI that we're using today is within this cycle, I'd suggest that we're over here along the slope of enlightenment. Now, for people that don't know this, this is made by Gartner. Gartner is an information technology and consulting firm. And they created this to showcase what the maturity of any new technology is. So the technology starts in the bottom left, time is on the x-axis, visibility in the market is on the y-axis. It's sort of based on Amara's law. Amara's law says we overestimate the effects of a new technology in the short term, but we underestimate it in the long term. Now, if any of you were at Dr. Whitfield's lecture yesterday, he showed something that was the peak of inflated expectations back in 2016, and even later when there was some prognosis that there were going to be no radiologists at all because AI was going to take over by 2021. And we're at a point where we need more radiologists than ever. So that was peak of inflated expectations. We're already beyond that. So I think we're now coming to the slope of enlightenment. So why can't we get to this plateau of productivity? Why don't we see a significant amount of use of these tools that can really help us with burnout, that can help us manage our patients better? And it's because in order to get there, we need best practices. And best practices are hard to come by. That's why we wrote that paper, is to try to provide the information that people have so that not everyone has to recreate the wheel, because it's sort of the Wild West out there right now. So why am I here going to talk to you about best practices? Have I written a lot of journal articles about it? No, some. But it's because of my experience, and that's what I want to share with you today. So I'm part of a large radiology practice, the largest radiology practice actually in the world. We do about 12% of all the imaging across the United States. And that comes out to about 56 million or so exams in every year. And with that, we started deploying AI back in 2016, and we have deployed a significant amount of this. This is numbers from 2024, so it's already out of date. But we have deployed and utilized AI in over 200 million exams. That is computer vision, that's language, so on reports and also on images. And with that, they've just given us a lot of experience, practical experience, using it hand-on, iterating on what works and what doesn't. So if we're going to create best practices, you have to have a framework. I find everything's much easier if you have a framework. So I thought the first step in creating best practices is determine what best practices do we have to create. So I created this Z-shaped process chart. Z-shaped because we have to think about it in 3 dimensions. Top dimension, horizontal axis, is what do you do before you actually deploy an AI system? There's best practices even before you're using it. The angled part of the Z is what do you do when you're deploying it? And then the sort of longer tail is what do you do after? And we have to come up with best practices for every single one of these. And then we have to share them because we shouldn't all have to recreate this. So we're going to talk today about 3 of them. And this first one was the one that I wrote in the paper. And it's evolved a little bit, but I want to show you through example how you can do this and how you can practically take it home and use it in your hospital location tomorrow. We're going to talk a little bit about bias as well. I actually changed some of my presentation last night at 9:30 because there were some new things that people have been discussing in the literature, and I think it's really important in this kind of conference for us to be talking about the latest and greatest and what's happening. And with that, there's a little bit of a touch on proving value. How do we prove that what we're saying we're going to do is actually happening when you're out there? Because that is not obvious. And it's certainly not automatic. So let's talk about the first one. How do you clinically evaluate an AI model before you even deploy it? Now, why do you have to do this? Why is it even important to validate? At least in radiology, anything related to images using computer vision has to go through the FDA. It's called a medical device. And there are some things that the FDA doesn't oversee, and that was defined in the Cures Act. But the Cures Act says that you have to satisfy 4 things to be clinical decision support. And one of those is, if you're looking at images, you're not clinical decision support, you're a medical device, and you have to go through the FDA. So everything that we're using, at least with images in radiology, has to go through the FDA. So if the FDA is already validated, and they're pretty cautious and careful to make sure things are safe, why do we have to validate? So this is an AI system that was on the internet. Pretty good model, actually. It was for predicting the bone age of a child. And you compare that essentially to the physiologic age of the child, and you determine, why are they slow to grow? So I ran this left-hand PA view of this child through the bone age model, and in 1 second, literally 1 second, it gave me this great output. Exactly what I would be looking for. Then I thought, well, what happens if I run something else through this model? What if I send it and I just grab this online, grabbed a couple of images of a mammo, and then I flipped it on its end. And I said, well, let me send this through the AI system. What is it going to do? And it used that image, and it predicted that this was a 13-year-old male. So validation is essential. You have to make sure that the tools that you're using are going to work on your patient population and your exam population, because that's not automatic. Just because they pass through the FDA does not mean that they're going to be generalizable and have the same kind of efficacy on your patient and exam population. So this is why we do the clinical validation before we even bring an AI model into our clinical production. And this is how we do it. 5 steps. And we're going to go through this in 2 examples so you can see how we do it for computer vision narrow AI, which is mostly what's out there, at least in radiology. Now, if you are making a decision about 5 things, you have to decide what you're measuring it against. What's your ruler? How do I decide if the performance statistics are good enough? How do I decide if there's too many false positives and pitfalls or not? You have to have a ruler by which you're going to measure these things. And because we are a clinical practice of many radiologists, we think of it clinically. If I have an AI tool that is a fantastic AI tool, really accurate, but my rads don't use it, it's useless. And we have seen this. We went to a hospital once where we were deploying an AI tool. We're deploying it, the way we deploy it is we go out and we train our rads on how to use it. We train our rads on where it makes mistakes and where it does well, because AI tools are not fully accurate, and we want to minimize bias. We want to give the radiologist the best mechanism to consume the output. And while we were there, we were showing our training to one of the people from the hospital administration. They said to us, wow, this is fantastic. Can you do this for 2 other tools that we bought that are just not being deployed? This is another reason why it's important. So let's go through these 5 steps, and we are looking at it, measuring it from the point of view of the user. The end user, are they going to accept and engage with the tool? All right, every time we're doing these, this is the mechanism by which we manage it. We're taking our data, which in this case for us in radiology are images in the report. We send it through the AI system. And these are generally older studies. We do it retrospectively so that we can manage this before we actually clinically deploy it. We get the results from the AI, computer vision. It usually gives us a yes or no. Is there a certain finding for narrow AI? And then we use a large language model these days. We used to use NLP to extract that same information from the radiology report. And then we compare the 2. And anytime either one has a positive finding, we send that through our AI radiology team of experts who clinically adjudicate every single one of these cases. If you don't adjudicate them, your LLM might be wrong, or the AI result might be wrong, even the RAD report might be wrong. So you have to do that to make sure your statistics are accurate statistics. And if you want to use terms like sensitivity, specificity, Positive predictive value. You have to validate your statistics. It has to be based on ground truth. Otherwise, you're just doing concordance and discordance measuring. So we do this, and then we send it through our process. So step number 1 of our process starts with, once you have your AI model, so this is an example of a brain aneurysm model. It's looking for an aneurysm in the brain on a CT angiogram. And we want to evaluate the model performance. Now, on the left is the model performance that was sent through the FDA. So we look at that. That's not wasted information. It's still useful. But then we adjudicate it again based on that diagram that I showed you of how we do it. And these are our statistics. Now, there's a few things that are different in what we do. First thing is we look at way more cases. If you look at the constellation of cases that are reviewed for an FDA clearance or approval, they're usually augmented. If the disease prevalence in this case for the FDA statistics is 36%, and that's because they want to analyze less cases to be able to identify what their accuracy is. And that's okay, but that's not real world. Real world disease prevalence is very different. And in our case, when we looked at across our entire practice, disease prevalence for brain aneurysms on CTA was about 5%. So very different. Now, why do I mention that? I'll tell you in a moment. The other thing that a lot of vendors used to tell me about, they would tell me about their ROC curve and their area under the curve and what that accuracy was, or they'd say, my sensitivity is this and my specificity is this. Remember our ruler. Our ruler is about radiology end user acceptance. The end user doesn't understand. We're not consuming sensitivity and specificity. We are consuming positive and negative predictive value. So positive predictive value means when the AI gives you a positive result, how often is it right? This speaks to the amount of false positives your radiologists are going to get. If that number is low, you're going to get more false positives. If the number is high, you're going to get less. That speaks very directly to how a radiologist feels about the accuracy of this model. Negative predictive value is the opposite. If the AI says that there is that one finding, if it's not present, how accurate is it? And usually negative predictive values are really high. They're almost always like 99 or 100%. And why is that? Well, because both of these statistics are directly related to disease prevalence. Positive predictive value is going to be lower if disease prevalence is lower. And negative predictive value is inversely related, so it's going to be higher if prevalence is low. And when we've looked at disease prevalence across our organization, it tends to be fairly low for any single indication, usually like 5 or 7%, sometimes less than 1%. And in that case, your positive predictive value is naturally going to fall based on the prevalence. And that could vary across our practice. So we recognize that when we deploy it in one location that does a lot of outpatient imaging versus another location, that rad may have a different experience with the tool because disease prevalence is different. Now, positive predictive value is also related to specificity and negative predictive value related to sensitivity, but they have less of an impact than prevalence. So important to understand the prevalence of where you're deploying and really important to look at positive predictive value. Now, in this case, you can see the positive predictive value was 52%, a little better than a coin flip. Not awesome, but at least better than 50%. All right, step number 2, we look at a metric that we call enhanced detection rate. It's something that we made up based on how radiologists feel about the tool. We want to know, not only from an end user perspective, but also from a business perspective, is this actually enhancing the radiologist's detection? Is it adding value? Because if it doesn't, why would I pay for this? If it's only finding the same things that the radiologist finds, I don't necessarily need that tool. So what we look at are the total amount of cases detected by a radiologist and the AI, and then we compare it to how much did the radiologist detect. So, and this is our brain aneurysm study. The total amount of aneurysms detected by AI and radiologists were 51. 41 of them were caught by the radiologist, which meant that 10 were picked up by the AI and not by the rad. So in the perfect scenario, this 10, if you divide it by 41, you would get your enhanced detection rate, and that number is 24%. 24% improved detection. That means 24% of the time, you're going to find patients where the AI will direct you to something that you might not have seen. That's fantastic. Step number 3, find what we call the wow cases. Now, wow cases are something that come from the enhanced detection. Any one of those 10 cases we look at and we say, is this something that a radiologist is going to be like, thank you for showing me this, because this would be easy to miss. We do this, number 1, because we want to show the radiologist before we even deploy what AI is good at, but we also want them to recognize that the tool is valuable, because there's a lot of inherent distrust between humans and computer systems, especially if they don't understand it. So we go through a bunch of these cases. This is a 74-year-old female, came in with acute neurodeficits, looking for a stroke. So in a stroke, in a CTA, we're looking for a vessel occlusion. We're not looking for an aneurysm. So it makes it harder to find, and especially on this axial image here, it doesn't look like there's an aneurysm because the aneurysm is in line on the axial imaging. You'd have to look over on the sagittal. But here's the heat map. This is the probability map that tells you what pixels are contributing to the AI result. And the probability map is pointing at this area that looks just like it's part of the vessel, but when you look on sagittal, you can see it's an aneurysm. This is one of those 10 cases that we didn't mention in our radiology report, but the AI picked up. We show these cases to our radiologists. Step number 4, categorize the false positives. I told you that the positive predictive value was 52%. There's a lot of false positives in that. Does that mean that the tool is going to be useless? Well, no, but it's very helpful to tell the radiologist, you're going to get a lot of false positives, but the false positives tend to fall into just a few categories. And if you didn't tell them that, and they see that the AI is calling a calcified dural plaque a brain aneurysm, the radiologist is going to immediately dismiss it. So you need to tell them, set the expectations about the kinds of things that the AI is going to be overcalling. And then you want to understand that balance, the balance between that enhanced detection or the wow cases and the positive predictive value, which especially with disease prevalence is never going to be 100%. Sometimes like this, it's 52%. So where does that balance lie? And when you make your decision, so we take all of that together and we make a decision. So in this case, step number 1, the real world performance was actually similar to FDA, which passed, and we thought it was acceptable. Step number 2, we had a very good enhanced detection rate, 24%.
Well, maybe while we're doing that, it's okay if I ask a couple of questions? Maybe you talk about how you all have such a large base and so much experience. How fast would you say you all are able to evolve? You know, the technology is evolving, but evolving across that landscape also probably has to be a challenge. If you're learning something, right, or something that you learn about it, you have to maybe talk about that while we're learning.
Sure.
Yeah.
I'm going to try to speak loud just so I don't get in the way.
Okay.
Oh.
Should be okay.
Before I started the AI division, and we have right now 5 full-time radiologists employed just to do AI. That's millions of dollars we're spending on radiologists not to read cases, just to think about AI. And before I started that division, I read the book, The Innovator's Dilemma. I don't know if you guys have ever read it. Really good book. It basically says that if you try to put an innovative technology within something that is very mature processes, and we've been doing radiology services, professional reading services for years, it's very mature, and our organization has 10,000 people in it. If I tried to put an innovative team that has to evolve quickly within the processes of that organization, it would have failed. And so when I did that, I asked our board of directors and our C-level team, I said, okay, I'd like to create this team, but we have to be nimble, which means we have to sit a little bit outside of the processes that we do today. And we're still doing that. And we've evolved quite a bit. The first time that we tried to validate a product, we did it by running a pilot, and it took 6 months. The next few times after we evolve that, because you should be learning every single time you do this, you should be saying, what can be improved? We now do it in 2 weeks. And now AI models, which convolutional neural networks used to take months, sometimes years to get trained and be available. And so you wouldn't see that many at a time. You could take a long time to review them in 2016. Now we can train a foundation model, a general model that is going to provide an input about the entire image that they're looking at, CT, X-ray, We can train that in 2 weeks. You have to be fast to be able to stay up with the industry. So you have to have a different process. Great question. Okay. Wow cases, a lot of wow cases, a lot of false positives, but we were able to categorize them and set expectations. So, right, this one, we decided it was worthwhile. We deployed this one. All right, let me give you another example. By the way, this is a singer named the example. So case number 2 is a pneumothorax model that we tested, pneumothorax on chest x-ray. Step 1, evaluate performance. You've seen this before. Left FDA, right our data. Look at the massive difference in the number of cases we had to look at. And that's because the disease prevalence, less than 1%. Really infrequent how often you're getting a pneumothorax and a chest x-ray. Now, this was across our organization. So we had ED, where you're going to see some. Inpatient, you're going to see more. Outpatient, very few, very uncommon. And so across our organization, really low disease prevalence. So what does that mean? Positive predictive value. It's going to be difficult, and it's very different from the numbers that were provided in the FDA. You can't trust that, even though they try to normalize it for a natural disease prevalence. So pretty low, and also the sensitivity was a lot lower. So not looking so good. Did enhanced detection, step 2, looking again at how many total cases were identified, how many of them were seen by the RADs? Well, all of them, every single one of them. How many additional seen by the AI? None. Enhanced detection rate, nothing, 0. So are you going to have any wow cases? Step 3, can't have any wow cases if you have no enhanced detection. So again, the balance, now this scale is not looking so good. Positive predictive value, pretty low. Enhanced detection, 0. Summarize and decide, pretty obvious in this one, not worth deploying. And what I didn't put in here, just for time's sake, is it also was missing things that were very large pneumothoraces. Our RAD sees one of those cases, they're going to dismiss it immediately. All right, I'm going to pause for a minute. I wanted to go into that. That's what I wrote up in the paper, was this process, and try to showcase to you what it looks like to actually deploy yourself. And I was going to go into more cases. I was going to show you how we do this for large language models that are only on language, and then how we can do it for language and vision models. And it's a useful talk, and maybe we can do it next year. But I think there's a more pressing conversation that we should be having. And it's because this question keeps popping up, and it's popping up in literature, and we're literature-based. We should be following evidence-based guidelines. And in some of the journal articles, it's suggesting that what they're actually seeing is that if you add a radiologist to an AI system, sometimes you get a worse output, worse than the AI on its own. And that has implications. And it's personal to me, but we need to take the personal out of it. And we need to make sure that we're looking at it based on evidence. So there are some things that I saw, and I was actually in Jim's lecture. It was an excellent lecture. If you guys didn't see it, fantastic. You have to go talk to him. Yesterday, and he showed some of those examples, and I saw some also in another presentation that I went to earlier this week. And I thought, well, maybe I could look at my data and what does our data show? And that's what I want to go into today. Now, we don't have everything, but we have some. And I want to start here with the enhanced detection. Now, going back to the brain aneurysm enhanced detection, there were 10 additional aneurysms that were identified. That means a 24% enhanced detection rate for our radiologists. Now, the other side that I didn't tell you about is there are also aneurysms, 13 of them, that were detected by the RADs that were not detected by the AI system. So that's a 34% enhanced detection rate where the RAD could be helping the AI system. What about here? Well, this one's more obvious, right? This was a 0% enhanced detection. And there were 33% of the time that we could have been helping the AI system. Now, is this true? Is it only for the 2 cases I've shown you? Well, no. Here's all of our data for these narrow AI models. And you can see I ordered it by, does the AI help the RAD? So what's the enhanced detection rate from the AI to the radiologist? And that's in green. And there's a good amount for most of them. By the way, that bottom model that had 0, we didn't deploy that. We went back to the vendor, told them it wasn't good enough, gave them a bunch of examples. And in the middle, it says pneumothorax 2. They redid their model, and look where it came to. And we said, we'll deploy that one. So AI can absolutely help the radiologist, but also it goes the other way around. And so what does that mean? It means that there's a Venn diagram of overall patient care and at least detection. That's as far as we got. And we haven't gotten to outcomes yet, but let's at least start with detection. And outcomes are going to be something that we'll talk about next year. But at least with detection, the two circles of what the radiologist detects and what the AI detects hopefully don't fully overlap. I mean, that's where the value is. The value is in those outside borders where the AI can enhance detection and the radiologist can enhance detection. We want to put those together so that we get the bigger circle, and we want to be able to take advantage of both. And if you have a case like we did with that pneumothorax model, where the enhanced detection was fully within what the radiologist saw, these models are expensive. I mean, we pay millions of dollars to run these AI systems, millions of dollars to run them every year. And if they're not helping, and I'll tell you that these systems do not significantly improve efficiency or capacity. So if they're not helping, why are you paying for it? You can't afford to do that in this day and age. So you have to be able to think about it in a different way. So let's go through a couple of examples. We were validating a chest x-ray model the other day. And here's a few cases where we can see the enhanced detection. Picture's worth 1,000 words, so it's not just about the numbers. It is about the images as well. So these were the cases by which some of those numbers came up. 77-year-old female comes in with a non-ST elevation MI now they're after post-CABG, and the RAD report gives all the post-CABG findings. And the AI system says, wow, if you look really closely, there's small bilateral apical pneumothoraces, something really important to identify, hard to see sometimes. And this was picked up by the AI system, okay, enhanced detection from the AI. Another 77-year-old female, different one, came in with altered mental status, and the radiologist said that there was nothing quite significant in the bones, actually written in the report, and AI system, edge of the film, that there's this fracture of the left humeral neck. Here's a case of chest pain, and the AI system said that there was no fracture, and the radiologist identified this mid-sternal fracture. Patient comes in with dyspnea. The AI report says that there is a right medial basilar opacity. Where is this opacity? Right here. Radiologist, no. That's actually the patient's hand overlying the lungs. So it can go both ways. Now, here's something that I always find is really interesting. And this is something that I learned in a book about neuroscience, that we have something in our brains called priming. If we are primed to look at something because someone tells us or we see it, we get much more sensitive in that area. So I think AI can help us with priming, and I've seen this in a lot of examples. So here's AI that says, in this image, there's a non-displaced fracture of the right ninth rib. Here it is. These can be very subtle on chest radiographs, hard to see, especially with all the other things that are overlapping a 3D image moved to 2D. So whenever we see this, I tell our rads, look for another, because there may be another. It doesn't mean that it's limited to this one finding. Now, the AI only found the one, but in looking more closely, there's another one that's very subtle. I think this would be hard to pick up if your brain weren't already primed to just look for those rib fractures and the associated findings, and not the 130 things that we look for in a chest x-ray. We found this to be true with every single AI that we used. That's where the two have the possibility to be better together, and the RAD did pick up both of these. So let's go back to our question, radiologist plus AI, where it might be not as good together, because in theory, all of those examples, or almost all of them, are theoretical. Enhanced detection of what the AI identifies and what the RAD identifies doesn't mean that the radiologist is going to accept all the times where the AI is right and discard all the times the AI is wrong. That it's not, because of this bias. Bias gets in the way. But we can be intentional about this. Let's dig into it a little bit more. I was trying to think about it, like, how would a radiologist plus an AI be worse than the AI alone? To me, it meant that radiologists were not accepting the accurate AI results. Right? If the AI gives you something accurate, the radiologist says, no, I'm not so sure. They don't accept it. And this is a certain kind of bias that's called distrust. We've got to get to the bottom of it if we want to solve these problems. None of them happen automatically. You have to be intentional about it if you want to resolve it, because a lot of the articles, I don't know that people are being intentional, and many of them are in the lab. It's going to be automatic that a RAD plus an AI system, anyone will have bias. That is an unconscious bias. We can't control it, but what can we do to make it better? Well, we have to understand what the bias is. What about this one? RAD plus AI is not as good as the radiologist. Well, that's a little different. I think that's when RADs are accepting inaccurate AI results. AI gives you the false positive. Remember, positive predictive value is kind of low. And that's an overtrust bias. So we've got to look at both. Now, I have a framework by which I like to think about it. So this is like a confusion matrix. A lot of you have seen this before. RAD, accuracy on the left-hand side, and on the top is AI. So AI results on the top, RAD on the left. Now, if they're both accurate, upper left-hand, hopefully we're going to get the right result on that, right? The AI says there's a pneumothorax, the RAD says there's a pneumothorax. Hopefully there's not going to be a lot of bias in there. We'll get the right result. If they're both inaccurate, the RAD says there's no pneumothorax, and there actually is, but the AI misses it too, kind of hard. Right, we're going to have to try to figure out how to find those in a different way, because that's not easy. But what I'm talking about is on the axis here, or the diagonal axis. So when the RAD is inaccurate, but the AI is right, we have to make sure in that case that the RAD accepts the AI result. And when the AI is inaccurate, but the RAD is right, we have to make sure the RAD doesn't accept the AI result. So how do you do that? That's not necessarily obvious. This is where distrust comes in. When the RAD, as we just showed, the AI was accurate, but the RAD didn't trust it. So we have to look at how do you mitigate distrust bias in that case. And then when the AI is inaccurate and the RAD accepts it, how do we mitigate the overtrust that happens there? And overtrust, I even split up into two things. A lot of people call this automation bias. They call it like the whole category automation bias, and we'll go into what that is. I like to split it up a little bit more because you manage each thing a little differently. And if we're going to be intentional about it, we have to understand it. We have to have language that tells us what's the underlying problem so that we can solve it. So I split it up into what I call automation bias and complacency. Both are when the RAD is over-trusting the AI system. Automation bias. Automation bias happened, it's when you're trusting the AI system too much, right? Overtrust. And it happens anytime with any human and computer collaboration, and it's unconscious. So it seems silly that we're doing it, but we don't even know. Like when GPS first came out, there were a lot of drivers that like literally turned the wrong way down one-way streets. They drove into parked cars. In this case, and there were a few examples of this. This was easy to find. Driving into a lake. Like, how do you drive into a lake? And they're like, well, the GPS told me to turn here, and I turned there. And it sounds ridiculous, but it's unconscious. We don't know it's happening. So what does that look like in imaging? We deployed an AI system it's a CAD-EX, so detection and diagnosis for breast cancer screening, and it was on tomosynthesis. And the model accuracy gives us a number. The PACS puts the percentage in. It's not actually a percentage, but you look at it, it looks like a percent. But it is out of 100. So 99 out of 100, the image on the left is breast cancer. That's the diagnosis. And 94 out of 100, the image on the right is breast cancer. And I don't know if any of you are breast imagers here, but these are cases that are fairly easy, actually, for a radiologist who does this for a living to dismiss. The one on the left are vascular calcifications. The one on the right is lumpectomy. Now, I'm an emergency imager. I haven't done breast imaging for a while, but certainly if like myself or maybe a referring clinician looked at it, primary care doc, they get this result because if it shows up in the PACS, and be like, oh gosh, this patient has breast cancer, and they're going to overtrust it. What we find is that overtrust happens more often the less you know about the underlying imaging. So if you're a subspecialist in that area, it's easier for you to dismiss a false positive than if you're a generalist or even a different specialty. And I bring this up because it's really important. You would think that no radiology AI tool could be used by a primary care physician or a emergency physician, especially these days when the accuracy is not quite there and we're still learning. Like, we're just not at that point yet where that information is to everyone. But that's not the case. If you go on the FDA and you look at their 510K clearance documents, if they have in their study, in their reader study, if they use any other physician outside of the specialty in which it's being, which that AI is evaluating, then that person can use the AI system. And all you have to do is prove substantial equivalence. And actually, you want to show that when the end user doesn't have the AI, and when they do have the AI, that they don't get worse. And it'd be nice if they get better. I mean, I could have my mom have the AI system and my mom not have the AI system, and she would certainly get better if she used the AI system in radiology. She doesn't know anything in radiology. She's a social worker. So, and she's a smart person, nothing against her, but that's not her specialty. And so the FDA actually does allow other specialties to use it, but we have to be careful about where you deploy, because these biases are present, and they're present in the end user even when they're an expert end user. But we have to be even more careful when it's not an expert end user. Now, we said AI has a lot of false positives. Let me show you what that looks like. This is related to the positive predictive value. So everything here in this yellow color are all of the false positives. And automation bias is related to false positives. When you get a false positive, are you accepting that result? That's automation bias. And the more false positives you get and the more you accept those false positive results, the more overdiagnosis you're going to do and potentially inappropriate treatment. All right, what's the other side? The other side is complacency. Complacency is also when you accept an incorrect AI result. It's overtrust. You're trusting the system too much, but you're trusting it when it's giving you a negative. It's saying there is no cancer, and you overtrust that. There is no pneumothorax. There is no pulmonary nodule, no intracranial hemorrhage. And it's very easy to overtrust an AI model. Why? Because the negative predictive value is so high. Remember, when it tells you the study is negative for that finding, it's usually right. Not always, but those numbers are pretty high. How do you find that needle in the haystack where it's wrong? And we could argue whether or not it matters, but if the radiologist would have called it correctly and then the AI didn't, you do want to be able to find that. Remember, we want those Venn diagrams to be separate. So this is complacency. This is actually, again, another one of the cases from breast imaging. I like showing these because these are deployed more fully across the U.S. And this model score was 11% on this tomosynthesis. And we were told by the vendor, and we actually found this to be true ourselves, that when the score was less than 20, remember it's out of 100, when the score is less than 20, it's very unlikely that there is a breast cancer. And you can almost dismiss it. And, you know, if you know that, and we've got to get through, we have this massive backlog of patients, well, you might read it a little more quickly and not even realize you're not paying as much attention. And in this case, it had an invasive lobular carcinoma. Now, our RADs picked this up, which is fantastic. Another case where there was no complacency in this exam. But it was a very highly trained subspecialist rad that had been trained very specifically on how AI works and where it tends to make mistakes. And that's what helps. You need those things to help manage bias. All right, so does this enhanced detection rate, we talked about there's enhanced detection. We know that. If the rad can help the AI can help the rad. We want the whole thing. But do we ever get that whole thing? Well, I showed you a few cases where, you know, at least that last one we did, right? But do we get it more in mass? And I don't have all of the data yet, but I have some. So let's go through some of this. And this is something that we did actually with Dr. Whitfield. And it was, we wanted to identify that these enhanced detection cases, if all of these things that we identified retrospectively, enhanced detection is a retrospective number, based on looking at prior studies. Does it actually happen when you deploy it? Maybe we go and we tell these hospitals, we're going to improve our detection by 20%. Actually, for rib fracture on CT, on outpatient rib fracture CT, it was 300%. Is that real? Like, does that actually happen when you deploy it? We didn't know. We hadn't done that. So we did that study where we looked at, before you deploy the AI, what is that enhanced detection rate? And in this case, this was for intracranial hemorrhage. We did it for a couple things. So this was intracranial hemorrhage. The enhanced detection rate at his facility for our RADs before deploying the AI tool, they didn't have access to it, 12.7%. Well, what happens after we deploy it? In theory, if you have bias and that prevents us from seeing any gain, it should be similar to that. And we looked at a lot of cases. So, right, like 1,600 cases here. And the next time we looked at 1,900 cases. And look at that enhanced detection rate now. We only missed one hemorrhage, and that is one that was a true positive. We validated these were actual hemorrhages. The AI provided the results, and the RAD missed it. Now, you would hope that it would be zero. Like, that's the goal. But sometimes there's technical challenges. We're not actually, in this case, we didn't have it rolled out to every single RAD. We still use the numbers. And there may be cases where you just miss it. You don't see it because none of these systems are truly integrated with our end systems. So is it actually, are we having a huge amount of automation bias and complacency? Well, maybe not. Like in this case, at least, we're increasing the Venn diagram some. Are we increasing it to its max? We don't know yet, but we're increasing it some. Here's another one that we did. We're looking at a generative AI. We have a generative AI that we deployed, which will summarize your findings into a holistic impression. And then the radiologist will look at that impression and they may change it or they may accept it, right? It's their report. They've got to make a change. So we wanted to evaluate the accuracy of that. Gen AI can hallucinate, can have all kinds of issues. So we validated a whole bunch of cases of these, thousands of cases. And what we found was the generative AI output on its own before the RAD looked at it. The error rate in that generative AI, significant, clinically significant errors that we thought would affect patient care, almost 5%. RADs love the tool, but it has an error rate, 5%. What happens when you add the radiologist and you look at their edited report? It decreased it down to 1%. Right, so another case where RAD plus AI are actually helping. And this is what we want to see, but it's not automatic and you can't get rid of it. You have to do everything you can to mitigate it. And that's the best we can do. And here's a couple of things that we do in our organization when you bring the two systems together. We make sure that the AI is transparent and explainable. You know, the AI does not look at every image that we look at. How do we know which images the AI even evaluated? Most AI systems don't even tell you. Well, how as an end user can you identify if the AI is right or wrong if you don't even know what it looked at? Like, that's insanity. We need to be providing this information. We need to be providing, what's the confidence of the AI? You know, these narrow AI systems give you a yes or no. Is there a pneumothorax, yes or no? Well, if their confidence is over, if that confidence for that AI finding is over a threshold, even by 1 point, they say yes. Right? They're very confident. If it's under the threshold, even by 1 point, they say no. Well, why can't we have some information about the confidence? It doesn't have to be a number, but maybe like a red, yellow, green light that gives us some information. You might want to be a little more careful on this. Maybe that data that it took in is a little out of distribution from the training data, and you should be a little more careful. That's the kind of thing we need to be providing to our end users at the point of care. Who should our end users be? Well, they need to be qualified. They need to be people who are at least in that specialty and hopefully in that subspecialty, and they need to be educated in how AI works in general and understand that your positive predictive value is going to be affected by disease prevalence, for example. So you may feel like there's different accuracy of the same tool, but in different situations. And then you need to monitor. You can't just say that's enough because remember, these are unconscious. You need to monitor the radiologist plus the AI, not the AI alone, to make sure that the radiologist is not having bias. And we do that in our organization. We continuously monitor the AI, but we continuously monitor how the RAD is using the AI. And when they're using it inappropriately, if they're not making, for that example, we actually look at how often the radiologist changes the impression, the summarized impression. We know there's about 5% clinically significant error rate. If they're never changing it or barely changing it, we have a chat with them to educate them. Right? That's the kind of thing you need to do to make sure that the two work better together. So I created this a while ago. It's like a bit of a vision slide, but if you want to take a picture, feel free. These are the things that I think we need to do more carefully to make sure that we are mitigating that bias. Nothing in life happens automatically. I like to think that nothing worthwhile is easy. And this isn't easy, and it's certainly not automatic, but it doesn't mean it can't happen. We have to be intentional. I gave a talk at RSNA, which is where I met Mel, and that talk was about what's the future of radiologists. You know, AI can do a lot of these things, and in fact now we're creating fully generated reports for X-rays and CTs, soon to be MRIs, drafted reports like a resident with AI that are very accurate. Is the jobs going to go away? It's going to change. If we did nothing, yes, the job would go away. But we have to be intentional and think about what value can we add now and elevate our role and continue to do that. That's how I like to think about things. All right, so that was pretty deep at the end. I want to end on something a little bit lighter. I use AI every day. I tell my kids to use it, not necessarily to write their term papers, but I don't think that AI is going to take over the world because we have the opportunity to make a difference. With that, I'd like to say thank you.
Hey everybody, John here. Thanks for listening to another episode. If you enjoyed what you heard here today, please check out our website at www.americancollegeaim.org. Sign up to become a member. Also, save the dates, October 9th and October 10th, 2026. We'll be back live in Chicago, Illinois at the McCormick Place Convention Center for our second annual live scientific session. Sign up at the website to attend. Until then, we'll see you all on the next Melvin Monday. Thanks for stopping by. See ya.